Paul, are you ready?
I'm ready, yes.
Okay, so good morning and good evening, and welcome you to this World River and Delta System Source to Sink webinar series. So today we invite Paul Schuster coming here to talk about the Yukon River, focused on the water quality monitoring. And so before I introduce Paul, I would like to mention our next week we have Zhixun come here talk about Lower Mississippi River and the carbon cycle. And then in July we will have a break, and then we will resume this talk series starting from August. So we have a whole bunch of good speakers already lined up in August. So all previous talk have already been archived on our YouTube channel. You can just feel free to use all the material for your teaching and research. The address, the channel is tinyurl.com/source2sink talks. And at the same time, if you follow our YouTube Source to Sink, and then you will get update every week, the notice about the future talks. And okay, Paul is a hydrologist in USGS, is the USGS Water Resources mission area. His research mainly focused on including nationwide study, acid rain study, Grand Canyon flood reconstruction, paleoclimate, paleoenvironment, pollution study in the glacial Wyoming, and the very important work is the Yukon River Basin in Alaska. As here you can see from his website, he has a very rich professional experience and accomplishment here. And so I think I will give the floor to Paul, and now you can share your screen and put the presentation mode.
Okay, are we ready?
Yes.
Okay. Well, good morning, good afternoon, and good evening, everybody. Thanks for coming today. This talk is a little bit out of the theme of the seminar. It's more about how we did things and not what we did. And I will at the end present lots of products and links to our achievements and our publications. But this is an overview of the first study of its kind in the Yukon River Basin. The Yukon River Basin, and that's a mouthful to say because we took a watershed approach to this study, and the Yukon River Basin is twice the size of California. So when you take a watershed approach to that scale, it's pretty challenging. It took us almost 3 years of designing this study before we actually collected a bottle of water. So, and again, this is not so much about sediments as it is about water quality. So first, I need to acknowledge everybody. The main thrust of this study was from the year 2000 to about 2005. There were many spin-off studies and spin-off projects after that, and we actually continue to work there to this day. And so we're going on 2 decades now. There were quite a lot of people involved in this study over the years. Obviously many people in the USGS, and we've had university participation. We've had NGO, Yukon River Intertribal Watershed Council was pivotal in this work. And the USGS, I don't know how many people on this call on this Zoom would know about the structure of the USGS, but in recent years, within the last 2 or 3 years, there's been a major reorganization in the USGS. Some of you might know about this, others probably don't. But I worked in the National Research Program, which was charged with designing and executing large-scale projects and programs too. That was the former NRP, because the NRP is no longer it no longer exists. We've been pretty much abolished. The NRP started in the early 70s, and there's been just a mountain of achievements and publications throughout those decades. But it's been disbanded now, and the USGS is now in a major reorganizational phase. So we had over 14 investigators in the Yukon River Basin project. When we realized the participation in this project, we identified that we needed to have a coordinator of some kind. And I suggested it, and I ended up getting the job. So, and that's usually the way things go. So we've had literally a whole family of investigators that came with their own ideas and research questions. And this is a list of them right here. And I'm not going to spend time listing everybody here, but you'll see this on the YouTube, and you'll be able to go back and review it. So, so the Yukon River and its tributaries present quite a challenge in trying to identify a baseline, a water quality baseline for the entire watershed. And actually, with technology, it wasn't really possible to do this until recent decades with GPS and all our new tools that we have. So I need to also talk about safety, because this was a major part of our project. Everyone on the project needed to be trained, and some of us had training already, others didn't. But there was just literally a whole classroom full of people that needed all kinds of training in the field. And we're very, the USGS has a very good safety record. And actually, on this project, in all the years we've been up there, we've had no, knock on wood, we've had no accidents, no serious accidents of any kind. Everybody's healthy and safe. We've done some pretty interesting training too. And one I'll just point out here is that last one, the pinch hitter training. I imagine some of you might know what that is, but we did a lot of bush flying during this project. And we found ourselves in very small airplanes. And we identified that it would be kind of nice, or at least comfortable, to know that we could land the plane if we needed to. Let's say if for some reason the pilot became incapacitated. So we actually took a class, and all of us on the project know how to land a plane if need be in an emergency. So these are the kinds of things we had to do throughout the Yukon project, and we had to keep renewing this training too. Okay, so let's get into the nuts and bolts of things. This project was actually a two-part project. One thrust was in collecting data that was based on fixed stations over consecutive years, and that we call that the fixed station part of the project. And the other part is the what we call the synoptic part, where we sampled the 43 major tributaries over a 3-year period, and we combined those data sets. The fixed station data was mostly for collecting baseline water quality data to identify what kind of river system this actually was. It's really amazing to think that we didn't know anything about the Yukon River up until about when we started working there in the early 2000s. And the tributary data supplemented the baseline data and was more looking at processes. In other words, like the baseline data told us what was there, and the synoptic approach told us why it was there and how it was there. So and the Yukon River, and I'm going to repeat this several times, the Yukon River Basin is very unique in terms of large river basins, and even within the 6 major basins for the Arctic, the Arctic Ocean, I should say. So we consider the Yukon River Basin as a benchmark basin for other Arctic basins. Also, this whole project is funded. Was the funding, the source of the funding would all revolved around climate change. So again, climate change was kind of the driver to this. I stole this from another talk in this seminar that was given back in, I think, in February. This is a publication that came out in 1924, and it was pretty much the first water quality assessment of the large rivers in the United States. Okay, I just thought it'd be interesting to show this because it took more than 75 years to get the USGS, for the USGS to do the same kind of approach on the Yukon. And the Yukon River Basin is a major resource for the United States. So what did ultimately drive the research? Well, obviously it's a warming Earth, and you know, the jury is in. Everybody knows what's happening. I think, you know, right now the thrust of research is revolves around how fast that the rates are changing, and also the feedback mechanisms, the positive feedback mechanisms that we are beginning to identify and how important they actually are. Here's just a few statistics that I know that, you know, people on this call or on this Zoom are pretty much aware of what's happening here. But one thing of concern in the Arctic that many don't really think about is the falling permafrost. And that the falling permafrost turns out to be one of the most important processes going on right now in the Yukon River Basin. I'm just driving it home here. I think this is from NOAA, but this just shows, you know, that the Yukon River Basin is right in the bullseye of the fastest warming parts of our Earth right now. And this just goes to 2004. We know that the last 10 years have been some of the warmest years on the planet. So why is the Yukon River so interesting? And basically, in the spectrum of all the world rivers, it's an end member. It's got some very unique characteristics. Characteristics that pretty much no other large river in the world has. For example, there's only one large, and when I say large dam, it's really not a large dam at all. It's a small hydroelectric dam in Whitehorse, Yukon Territories. But the entire 2,300 miles of the Yukon River from headwaters to the Bering Sea, there's only one bridge that goes across it, and that's the bridge that the pipeline runs through. There's no cropland, there's no very large cities as you know as we know them, and you know, and the population is crazy low. And you know, in terms of per capita, and yet it drains a large area, twice the size of California, so it just has a lot of unique characteristics that we feel as hydrologists and people who like to study large river systems that this was the place to go to, especially for climate change research. So the river's unique and very important to not just scientists, but to the people that live there. This is subsistence living that you know that I've never seen at a scale on all the travels that I've done. People literally depend on bagging that moose in the fall. Without that, they have no meat in the winter. And it's a very interesting area of the world because it's kind of first world and third world like wrapped into one, and where you can have your cell phone, your internet, and everything, but yet you might not have running water in your house, or you might not have a floor that's wooden. It might be dirt. These are the kinds of contrasts that exist in the Yukon River Basin. And it is the largest untamed river in North America. And that's pretty much, that's a big thing to say. Every river that we have in the lower 48, every large river has been very drastically, let's say, reprogrammed, for lack of a better word. It's been levied, they've been manipulated for man's needs. In the Yukon, that's not the case. And hopefully it's going to stay that way for a while. The other large rivers like the Mississippi, they act more like a string of lakes than anything else, with the blocks and the way they control the rivers. So we had some preconceptions about the Yukon River Basin before we even set foot there. We knew about the feedback mechanisms. That was something that we really are concerned about. So a lot of our research was geared towards trying to quantify and qualify these feedback mechanisms. And this is kind of a schematic, a demonstration of what we mean by a feedback. Warmer temps mean more metabolism, mean more carbon dioxide from the rivers, and also the thawing permafrost contributes to that. Then you get more carbon dioxide in the atmosphere, and that's more greenhouse gases, which makes more warmer temperatures, and so on and so on and so on. And let me point out too that another I guess characteristic of this Earth that people don't understand is that 13% of the entire Earth's surface is underlain by permafrost, and that's important when we're talking about the scales of these processes. So again, I'm gonna kind of reiterate that that this was a two-part study. Again, the baseline data was collected by fixed stations, which are represented by these red triangles. So these are fixed stations that they repeatedly went back to for about 8 times a year at each site for 5 years in a row. And I want to point out too that the most important of all these fixed station sites was this station right here, Pilot Station. That's the operational outlet of the Yukon River Basin. And we concentrated a lot of process-based studies there. There's a lot of other researchers that work there. The Woods Hole has an established program there called Arctic GROW, Great Rivers Observatory. That's one of their sites. And so Pilot is important to us. It's the operational outlet, and we call it that because it's 100 miles from the Bering Sea to Pilot Station, but yet it still can be tidally influenced, or anything below Pilot can be tidally influenced. So that's why and there's a lot of logistical problems like going out to the Bering Sea and establishing that as your basically your discharge point for the entire basin. There are 3 distributaries in the Yukon Delta that distribute the water into the Bering Sea, and it's very swampy, it's very logistically challenging to do a study in the Delta. But yet we've got some ideas there, and we haven't given up on that part, on that kind of hole in the whole research project. Then we did intensive sampling, where for 3 years in a row, we chose 3 different reaches of the river because it's 2,300 miles from the headwaters that consist of the lakes, the glacial lakes from the Juneau ice field, all the way in British Columbia near Whitehorse. So right down in here, These are where the ice fields are, and then they drain into glacial lakes, which end up in being the Yukon River. And it's kind of ironic almost that it's only 60 miles to the ocean, but yet it goes 2,300 miles all the way from west to east out to the Bering Sea before it hits another ocean. I always found that to be an interesting fact about the Yukon River. We took us 3 years to do this because just of the length of the river, the seasons were too short, and we couldn't do all our water quality work for the entire reach in 1 year. It was just logistically impossible. So we broke it up into 3 different years. So we focus on carbon, and that's because of the climate change. The climate change element of this research. We talk a lot about the great debate about where is the carbon going, and this is the source and sink thing. Is the carbon going as things get warmer? Will the carbon go out with metabolism in the soils and the falling permafrost, or will it go out with the rivers as the permafrost thaws and flow paths change, and the basic hydrology changes up with the system, all driven by warming temperatures. So there's a kind of a debate going on. It's how much is going up or how much is going out, but likely it's both. And right now it's not. It's probably right now it's probably more going out by hydrology and surface water transport. But we see in the future that may change, that may shift to about going up instead of out, because the metabolism of the microbes is increasing every day as we speak, as it gets warmer and warmer. And that's CO2 directly to the atmosphere. Let's see here. Another thing I want to point out too is that carbon likes toxic metals, and I'm going to go into this a little bit as a bit of a side project of part of this entire study and the research questions that we had. It's also a nutrient. It's the base of the food chain, and this has major implications for the aquatic health of the Yukon River Basin. The Yukon River Basin is so huge that it's a global source of carbon. And I sometimes like to say that the YRB is literally a pump. It's a carbon pump into the Arctic Ocean. It actually is. I think I got a slide coming up that kind of teased into that. So carbon dioxide and methane emissions were measured. And they were measured in a way where we're trying to identify sources and sinks. In other words, the wetlands. There's a large area of the middle of the Yukon River Basin called the Yukon Flats, and that's a major source of carbon. And then there's talk about it becoming a sink. And in terms of the carbon dioxide as a gas, being created as a gas in the Yukon River Basin. You think of it like this: the Yukon River freezes in the late fall, and it melts in the spring. And during that entire time, carbon dioxide is building up underneath the ice in the river. And within a few days of ice out, with a breakup, the Yukon burps, a major source of carbon dioxide to the global carbon dioxide cycle. So that what I was leading into was is to put it in perspective. We measured through carbon dioxide measurements that the Yukon River is pumping out more carbon than all the 5 other major rivers draining to the Arctic Ocean. So it's unique in that way, in that it is an M member, and that we need to watch the Yukon River. We need to monitor the Yukon River, because as the climate continues to warm, this positive feedback is just going to keep getting more and more positive. So let's talk a little bit about permafrost, because permafrost is kind of like drives what we see in the system. When we have permafrost, it's a barrier. I can attest to the fact that it is really a barrier. It's harder than cement, and nothing pretty much gets through it. So when the barrier is there, the hydrologic system is shallow and lateral. And so it picks up a lot of organic rich nutrients and carbon and metals. And as the groundwater moves towards the stream, and also the surface water, when in the springtime, all the snow melts. So you have this kind of pulse of nutrients and metals and you name it. It's coming out in a short period of time, and a lot of it at the same time. So what if you take the permafrost away? Well, then you've got changes. You've got flow path changes. They deepen. The superficial groundwater flow paths are now going through mineral horizons, which kind of filters the water. The regional groundwater paths are now going through parent material, and there's no more aquitars. There's no more barriers. So there's major hydrologic changes to the basin that are happening now, and we're trying to capture that in the water quality data. So our sampling campaigns were two types. There were the fixed stations and also the synoptics. And I know you've heard the term synoptic. What we did with synoptic, it's not a true synoptic. A true synoptic is where you follow a parcel of water and you watch it evolve and change as it moves through different regions, systems, geology, geomorphology. So we kind of use the term synoptic loosely. But we had a list of criteria to choose our water quality sites because of the scale was so large, and we just needed to pare the things down and just do what was realistic. So these are the list. This is the list here, and I'm not going to go through every point here, but you kind of get the idea that we had to follow kind of a protocol so that we had to limit the amount of sites because logistically we just worked on such a large scale. So this is more about the fixed stations. We designed a fixed station sampling campaign such that we captured different I'd say conditions, and also we needed to collect more data during one part of the year than another part of the year because of using things like tools like LoadEst for estimating loads, getting the most accurate output from those programs and those tools. So the sampling schedule went from 2001 to 2005. We did one under ice measurement, which were always challenging. And we were out there, every 2 weeks after ice out. And it worked out to about 7 or 8 samples per year. So, and when did we get the water? Well, again, we're trying to capture different hydrologic regimes. So high water would be during ice out, during breakup, and then low water would be in the fall. And then we would in August, that's the rainy time of year, we would try to get sampled during after rain events. So that was the approach we took with when we got the water. And so how did we get the water? We didn't just fill bottles. We had our USGS protocols and methodologies that we use. We use a lot of established equipment. These are well-established techniques that we use. And we work in all kinds of weather, as you can see too. The boat you see there is carrying what we call the D96. It's the water quality sampler. We also call it the bomb because it looks like a bomb. It's very heavy because we need to. These are large rivers with very strong current, so we need to make sure that we keep the sampler vertical profile. And then this is a schematic of, how we do things, how we actually sample the river to get a representative sample across the cross section. This is very important for our sedimentology work because, as everybody knows, with sedimentology, it's not just it's never homogeneous. It's a heterogeneous system when you think about sedimentology. You've got what they call bed flow or bed movement, where the bed actually moves, and then you've got changes vertically with sediment concentrations. So in order to get the most accurate measurements for sediments and for solutes and particulates, especially carbon, we have to do this approach. We call it EDI, equal discharge increments. This is highly intensive logistical work. It takes hours to do one measurement, but yet it's worth it all. It's worth all the effort because we get a compositive representative sample. And we use the latest technology. Acoustic Doppler current profiler basically uses sonar off of particles, and it's very reliable, very well established throughout the USGS community. Also, I think most other scientific organizations also use this technology now. Long ago, we used to do this by hand, manually, put on waders, and obviously you can't do that in a large river. So when acoustic Doppler was first brought on, it really opened up the world of hydrology. Okay, so the intensive sampling was what we call synoptics, and we identified 43 major tributaries from headwaters to the outlet. And we did this over 3 consecutive years, as I've mentioned. And we did twice each year at each of these tributaries, at high water spring flush and at low water base flow in September. This gave us an idea of the inputs to the basin and which tributaries actually made the Yukon River what it is in terms of water quality. Okay, and like I said earlier, there were a lot of spin-off studies that happened during this time. And in the year 2009 to 2011, a group of us got together and we designed a process-based consecutive year study at Pilot Station, where we stayed there for 6 weeks from early May to mid-June. And we sampled daily. And so this work ended up helping us identify processes in our water quality database, our fixed station baseline water quality database. It helped us to understand the processes behind what we were seeing throughout the annual year. And so we had to, living for 6 weeks in Pilot Station was very interesting. Lower left here, that was where we lived, and we set up our laboratory in there. And the river is only about a half a mile away, not even that, it's probably a quarter mile from this building. And lots of interesting field tales that we had. This is one of our, we call this the caravan, and it was basically how we shuttled our gear to the bush villages. And the Yukon River is what we call a flashy river. So this is a hydrograph of 1 year at Pilot Station. And I'd like to show this one because no year is the same in terms of breakup. Every year is different. And the reason is mostly because of things like ice jams. Right here, where we can see what happened here during this year. I can't remember which year this is. I can't see it. But there was an ice jam on this year. As you can see, it was going up as the snow started to melt, and things were going up, and then all of a sudden we got a block, and things started going back down again, and the block and the water was pushing up behind the ice jam, and then the ice jam broke like a dam, and it shot up and stayed up for days and days and days. So those are the kinds of dynamic situations we have in the Yukon Basin. And we did some crazy things. This is a colleague of mine from Woods Hole. There's a kind of a window during the year where it's really hard to do any kind of water quality work. And why do you think that is? Well, you're looking at it. It's the breakup. And during the breakup, you can't get a boat out there. You really can't do much. But we knew that hydrologically and in terms of water quality and geochemistry, there was a lot of going on at this time. So we were trying our best to capture that. And here's a slide of Rob that with a sampler that we designed to get out into the river, into the main flow as much as we could with safety in mind. So, and Rob he is tied in there. So if something were to happen, we'd be able to pull him back out. And this is just an interesting thing that happened during breakup during our pilot station study. We actually saw a moose going down the river on the ice, and we couldn't believe our eyes when we saw it. And the most incredible part about this is that moose that I have circled there, there's another moose that you can't see that ended up popping out of the water as they were drifting by us. I have no idea how the moose do this, but the locals tell me that this happens a lot actually. And how they get on the ice and why they're on the ice, I don't know. Maybe they're just taking a free ride, like a bus, down to areas where there's more food. I really don't know, but I found it to be fascinating. So we did a lot of work with outreach, and we involved the communities. A lot of citizen science. This is just one example of one school district that I worked with, where the kids actually got involved. They actually really collected real data, and we processed it. We QA/QC'd it. The students were amazing, and this happened throughout the Yukon River Basin. Eagle is just one example. It was a very rewarding part of the entire project. And we had volunteers everywhere. Everywhere we went, somebody wanted to help. And we found out that was really amazing. The stewards of the Yukon River Basin, the people that live on the river, they cherish the river. They know its value in terms of culture, in terms of life, and they want to know more about it, maybe even more than the scientists. And I'm trying to get rid of this top bar here. Oh, no. All right. Well, the citizen-based science is very important to us. And this was facilitated by our partnership with the Yukon River Intertribal Watershed Council, which oversees over 76 different tribes throughout the Yukon River Basin, all the way from Canada, all the way down to the Bering Sea. We actually published a paper based on citizen science on how successful it had been for us over the years. And that paper is listed here, and I've got the address for you there, so you can look it up. But that was, again, a very rewarding part of the program. And we very much enjoyed working with all the locals and the elders, and their knowledge on their oral knowledge of the river is just amazing when you listen to the elders talk about things. And they put things in perspective too. I was once talking to an elder in Kotlik, which is out by 20 miles from the Bering Sea. And he said to me that a couple years ago, it rained in January. And I thought to myself, well, okay, that sounds interesting. And he says, no, you don't understand. It never, ever rained in January, ever. And what he meant by that was that in his oral tradition, he's talking about hundreds, maybe thousands of years in their oral knowledge that they don't have a recollection of it raining in January. So those things are important to me as a scientist. The melding of TEK, traditional ecological knowledge, and modern science. So again, one of the things that we recognized right away, one of the challenges was a scaling problem. In other words, how do you go from small scale studies of collecting water quality data and scaling them up to see if these processes happen like at a larger scale? So as we were going through that thinking process, I started to think about Mercury and how I knew from other studies and other programs I had been in how important carbon was to Mercury. And being that the Yukon River Basin was a carbon pump, I started designing studies to investigate the Mercury story in Yukon River. And these are a couple of papers that came out recently within the last couple of years. The bottom one there, that's a paper that came out recently in Nature, and that was Kevin Schaefer, who gave a talk back in the winter on this particular subject, and some of you might recall that talk. Earlier on, the precursor to that study was a study that I designed with Kevin and many other people to look at the stores of mercury in the permafrost, and that came out in GRL. And so these are these side projects that I kind of talked about earlier. Just a little background on mercury. Mercury is a neurotoxin, as many of you might know, and it occurs naturally from volcanoes and bedrock, but it also is a major pollutant from man, from coal and cement smelters, also biohazard material or biomedical material is another big source. And it comes in many forms too. You might have heard the term "mad as a hatter." Well, that was from the hatters that cured the hats in the 1700s. They used mercuric chloride, and it invaded their nervous systems and it made them go mad. So, and the most important part of our type of mercury is methylmercury, and that is toxic. It's a neurotoxin. And when we talk about mercury in the environment, really what we're talking about is methylmercury. Okay, mercury in the carbon cycle. I just wanted to just pop this one up real fast because what I want to point out here is mercury acts like, or it mimics nutrients, and it binds to organic matter. And once it binds to the organic matter, it's kind of hard to get rid of. And it can be transported through processes like we talked about earlier. And it enters the food chain. And the Yukon River Basin is kind of set up for methylation of mercury. And also I want to point out that our research in mercury in permafrost, kind of quickly, we realized that this is a pool of mercury that people haven't really thought about in terms of the mercury global cycle. And it's a significant pool. And it's probably going to change the way we think about the mercury cycle, the global mercury cycle, as we incorporate this new data into the models that we use right now. So what we learned about mercury is that it's vulnerable to the Mercury is vulnerable to release as permafrost thaws over the next century. And also that we need to reevaluate the role of mercury in the global cycle. And then the modeling efforts that Kevin did later on, we concluded that basically, in a nutshell here, we're okay if we stay with the low emission scenarios. We're not okay if we don't. And we're gonna exceed the EPA guidelines by the year 2050 for fish. Things like that are going to happen if we don't do something to curtail these scenarios that we're talking about. There's a couple things about methylmercury within the Yukon River Basin. The good news is that there are low levels at this time. The bad news is that the Yukon River Basin, as the kind of basin it is really set up with climate change to be a major potential for methylation of mercury. So the wetlands that we see now, mercury is the potential is going to go up in the wetlands for mercury to be metabolized into methylmercury. So, also the Yukon River Basin has the three ingredients. It has a source, which is atmospheric. It can be transported because of the high organic matter very easily. And it can be transformed to methylmercury because of the warming climate. So I'm going to, right now, this first slide, there's going to be 5 more slides, I think, that look like this. And these, I'm going to blast through them because the first slide is the publications that you can get that contain all the data for what I've just talked about in the last 40 minutes or so. And I have the URLs are all listed here, so you can go back into YouTube and you can find them. But the major publications that came out for fixation are listed here. And then the major publications for the synoptics are also listed here. And then the relevant publications, there are many, many of them. There are, and I just concluded the ones that were relevant. There are many others that worked off of our databases. Many other researchers that grabbed our data and used it for their own kinds of research. And the last publication that came out was back in September, and that was the one with Kevin and myself and other people on the impacts of mercury, which this paper would not have been possible if it wasn't for all the previous research. Okay, so what was our product? Our product was the baseline. Okay, this is the first baseline established by scientists for the Yukon River Basin, first water quality baseline. It will be used in the future, just like that report I showed you earlier, where that report was 75 years ago, and yet they still refer to it as their baseline water quality data. We found that our product, our baseline, is going to be used in the same way. And it also will be used to measure as a way to measure future change. Again, hence the word baseline. So some other things that we learned along the way is that the Yukon River is actually a rather pristine, clean river in terms of rivers, large rivers of the world. We hope it stays that way. And it has advantages because of that for conducting studies that we know that climate change is impacting the river systems. And again, I talked about the up and the out earlier. We're seeing things like the breakup is trending towards earlier dates, and the ice over is trending towards later dates. This actually affects the communities. They use the Yukon River river systems as their roadways. They don't have any roads in the Yukon River Basin, very few. We also have been noticing changes in the groundwater, and this again goes back to that thawing permafrost and the barriers and the aquitars, and so we're seeing that. There's a paper by Michelle Walvard, a USGS colleague, that talks about that. There's another paper out that looked at tritium and actually concluded that that the Yukon River Basin, even with its size, has a very short residence time. It's only on the order of 15 years. Now, we think that residence time is going to drastically increase as the groundwater flow paths get deeper and deeper. Again, this all relates back to major processes that are being impacted by climate change. With our work with carbon, we really went into great detail and effort to identify all the different phases of carbon, the kinds of carbon that you see, whether it's labile, whether it's not, and so we've got a good map of the carbon in the Yukon River Basin, especially as it relates to water quality and aquatic health, and the general health of the system. We found that we had a microbiologist that worked with us, and she did some experiments with looking at microbes in permafrost, and realized that they actually are, some of them, like about 10% of them are actually alive, and so they can actually metabolize. And this has major implications for the positive feedback that I talked about earlier. And again, these changes have a major impact on the global mercury cycle, which is another conclusion that we made through our 20 years of research. I think that's about it. And I just want to wrap it up with I do this because I believe it's all about our future generations. And I hope that that this data will be used by my descendants and future scientists, and will be wiser for it. So if there's any questions, I'll give it back to Paul.
Oh, thank you, Paul. This is a very, very interesting and informative talk. And thank you so much. So now let me now open the floor to all the audience. If you have any question, you are able to unmute yourself now, and you can go ahead and ask Paul. Okay, cool. Okay, Reinhard?
Yeah, hi, Paul. This is Bernard.
Hello.
Yeah, thank you. A great effort, really pioneering study on the Yukon. Paul, I have two questions for you. First one is, there's a lot of legacy contamination in the basin, from military activities, from kind of poor waste management in these sparse communities. Could you speak to that and the effect on water quality in the Yukon? And
yes, I can. Yes.
And the second question I have for you is, you took a lot of samples during these intense sampling campaigns. Are they still accessible? Are they stored somewhere? And accessible
the ones that can be preserved are still they're archived. But other samples, obviously, they're perishable. They can't be they have a shelf life. So a lot of the carbon samples are at a shelf life. They're all gone. But the heavy metal samples, they're preserved with acid, so they're still archived. All the permafrost work, that's all archived.
How about the sediments?
Sediments are archived. Yes. If you think of it as perishable and non-perishable, then that pretty much answers your question. Yeah. And they are archived right now. And if you go through the proper channels and people have interest in the archive samples, I'm sure we can find ways of getting them to people if they need them.
What's the USGS policy on archiving? I mean, is there an expiration date on these samples? Is there central archive?
It boils down to budgets and, whether we have the facilities to keep them and the space. So now there is a bit of a problem that recently, because the National Research Program was disbanded. So our facilities are in question now. So I would say that if you have an interest in some of these archive samples, the sooner the better, because I can't predict what's going to happen down the road here.
Yeah, please let us know, before they get thrown out. We'll transfer them to Woods Hole and store them here.
Yeah, okay. All right, yeah. Now, to answer your first question on what you're basically asking is point source pollution versus non-point source pollution. And you could easily design your study to answer point source pollution questions. All right. And I will tell you, there's a lot of point source pollution on the Yukon River. Okay. And it's a lot of some of it's pretty interesting. You know the city of Dawson? Everybody knows Dawson, right? The famous city of Dawson. Do you know that they still directly discharge their effluent right into the Yukon River? Untreated. So, we're in the 21st century, yet these things still happen on the Yukon River. And we actually we were looking for emerging contaminants and POPs and endocrine disruptors from their sewage system. So we actually designed a small little study to see if we could capture that. And so we sampled.
But are these Paul Leo's kids on this picture?
Well, yeah, these are kids from Pilot Station.
Oh,
So
okay.
yeah,
It's pretty nice. Well, and actually, it's allowed to swim there, isn't it?
What's that?
Is it allowed to swim there? Can you swim there?
Well, you could if you wanted to.
Okay.
I don't think it's a little cold and it's kind of mucky.
Okay.
I
I can't swim.
Yeah, I don't think I've ever seen anyone actually swim in the Yukon River, but so the point sources in the Yukon are pretty interesting. There's a lot of military, as you mentioned earlier, a lot of military waste laying around, but their major point source pollution problems all stem from sewage and from trying to manage their sewage systems. And so, by the way, when we did our sampling just downstream from Dawson, we got no hits. So you can always say, use the. You can use the word. You can use the words. Solution. Or no, what is it? Dilution is a solution to pollution, but that's really not the case with the Yukon. Although you can imagine it could be, but so I hope that answers your question on point source pollution.
That's interesting. So Paul, you mentioned that because there's all the carbon we understand with the melting could be released to the river. At the same time, because the temperature get warmer, it could also new carbon introduced to the water. And so overall, the old and plus new increase, as you said, is up and up. So do we have a good suspended sediment discharge data?
There is a database on sediment on sediment discharge, and that's in those publications that I included at the end of the talk. So those data sets are all buried in those publications. And so there's like each one of those publications for the fixed station data. So there's 5 of them for each of the 5 years. And within each one of those publications are probably about 20 different data sets and one of those data sets is a sediment data set. And we don't just have sediment concentration data. We have sediment water quality or sediment quality data. So we measured the metals in the sediments.
Oh, okay. Because with continue that, the warming, so we really need that continually and disrupt monitoring observation from those high latitude river systems. That's a big need.
Right. Yeah. And, the other river systems, there's 4 in Russia, Siberia.
Yeah.
These other river systems, in terms of their water discharge, they dwarf the Yukon River. I mean, the Lena is huge. It is a huge river, and yet the Yukon's pumping out more carbon than the Lena is. So, so the Yukon is a very valuable, in my perspective, in terms of science and science research, geared towards climate change.
That's very interesting. Any other questions?
Hey,
Hugh?
yeah. Hey, Paul.
Oh, hey, Jin. Yeah, yes.
Yeah.
Jin, yeah, go ahead.
Very, very interesting talk. Thank you very much. I just came back from Alaska a week ago. It's a very fascinating system. And I have 2 questions for you. First one, you have shown the total carbon export from Yukon River, as I remember, about 8 teragram per year. Do you have information about the ratio between DOC and DIC? So what is the fraction of
Yes,
DIC
we have
that?
we have fractionation data on we took apart the carbon atom. We really did took a lot of effort. One of the major researchers, I don't know if you know his name, but he's internationally known, was George Aiken. And I don't know if you knew George or not, but he's international. Well, he's passed away now, but he designed the carbon part of the program. So we fractionated the carbon into all the different, the different the hydrophobics, the hydrophilics, the transphilics, the low density. So we've got the data on that too. That's all public. But what we found in terms of carbon in general was that the system is dominated by POC and not DOC. So, and that's interesting when you start to think about mercury dynamics, because we don't know much about how mercury binds with POC, with particulate organic carbon. We know a lot about DOC, but not much about POC. So that's a kind of a research hole right now. And I know there are investigators working on this.
Yeah, the reason why I'm asking about this is because we know the Mississippi River, the carbon export has a ratio between DOC and DIC about 1 to 4. So let me think. Yes, 1 to 3 and 4. So the majority of carbon exported is DIC. So I was just wondering how the Yukon, in terms of carbon fluctuation between DOC and DIC looks like. And so anyway, my second question is, do you guys have an idea about which tributary make last greatest contribution to carbon in the like a Tanana River?
We know them. That's why we did the synoptic studies. Those 43 rivers. We needed to know what tributaries like contributed to the system in a large way. And I got to tell you, the one that sticks out by far is the White River.
It's White River.
The White River, and that discharges. It's still inside Canada when that discharges to the Yukon. But the Yukon River is actually clear until you hit the White River, and then it becomes that glacial flower, kind of muddy appearance. So the White River is a major tributary. The other two rivers are the Porcupine and the Tanana. And the Porcupine is a major source of carbon because it drains a huge wetland area, like the size of Connecticut, the state of Connecticut, okay? The Tanana River is a major inorganic contribution in terms of glacial flower because it drains all the glaciers. Mm-hmm. So you've got three major rivers that change the Yukon.
Mm. Very interesting. Thank you.
Yeah.
Great to talk.
Yeah.
You're welcome.
That's very good. Paul Bahad, the Chinese government from 1990s, every year, the Ministry of Water Resources or something, they publish the annual report for their national rivers, like at least 10 large river system. And I'm not sure, maybe in US, if USGS in future can do the similar thing, like publish like the Mississippi River, the Colorado, the Columbia, the Yukon, pick up the 10 or something major river about the annual report about the water discharge, sediment, water quality. That would be a fantastic information.
Yeah, well, it does exist, and not so much in the form you talk about, but that we have these programs on these large rivers in the lower 48, especially that are year round monitoring. And and they publish their annual reports. The Yukon, the USGS is basically designed in terms of water science centers. So almost every state has a water science center, and each water science center is charged with putting out an annual report. So it may be broken up because of it being a state-based kind of counting system, but it's still all there.
Yeah. Okay. Cool. Okay. Thank you, Paul, very much. And as always, this talk is also available archived on our YouTube channel. So if somebody, if you can recommend it to your friend, a student, you can send a link to them. So, okay. Thank you so much.
Thank you.
Okay.